When we were looking at gravitational potential energy originally, we used a force equal to mg. Right? We said that if we apply a force over a distance, we would have to apply a force equal to mg, and we would apply that force over a distance delta y. And the work that we did against that force would show up in the system as a change in gravitational potential energy. Then, from that, we defined our gravitational potential energy as mgy. If we want to use the more correct version of gravity, we can do the same thing. We can say that if we are lifting an object against gravity, we'd have to apply a force of this magnitude, and we would apply it over a distance, again, delta y. But in this case, we can see here that as y is changing, the value of the force is going to change as well. So here's our force that we're applying. This is a force equal to the force of gravity. This is the force that we have to apply to lift an object against gravity. Because we're lifting something upwards, I've gone ahead and used y here, and we're going to lift it from some y initial to y final. These are all constants. We're integrating y to the negative 2 power, and so we know what that integral is equal to. We can evaluate at the two endpoints. This term is multiplied by both of these terms whenever we evaluate these 2 points. Like before, the work that we're doing against this force is going to show up as a change in gravitational potential energy, which more specifically is going to be the final gravitational potential energy minus the initial gravitational potential energy. And so we can see we can define this term here thusly, we can define this term here thusly, and generally speaking, we can say that the gravitational potential energy between two objects that are far enough apart for which this distance between them is changing enough that there's a non-trivial amount of change to the gravitational force, we can say that the gravitational potential energy is thus. Here I used y because I was imagining going in the y direction, lifting an object up from a planet Earth, for example. But what we'll go ahead and do here is generalize this a step further and let this be an r, because if we go out in any radial direction r, we should have a change in gravitational potential energy as a result. So we found the equation for the gravitational potential energy between two particles. We would say that this is the energy of interaction between these particles. So that when they that there's an energy representing the interaction, the force of interaction between these two particles, due to the gravitational force that each would exert on the other. Notice that this gravitational potential energy is negative. See, there's a negative sign right there. It's negative because the particles are bound together. This is a bound state. The two particles are held together because of their mutual attraction. So that's a negative energy. That means that you'd have to put energy in to proactively pull them apart, because naturally gravity is an attractive force, and naturally the particles would want to pull back together. So you would have to input energy into the system in order to separate the particles. If you have some system of particles where you have multiple particles that are would be interacting with each other through gravity, then the gravitational potential energy of that whole system would be the summation of all the pairs of particles. You'd be adding up how much energy you have in each pair of particles. In this expression here, you get a factor of 1/2, because if you're using a summation, you would include a sum of the interaction between 1 and 2, and then also the interaction between 2 and 1. You'd be overcounting, and so that 1/2 fixes it for you. In practice, you would add up each term. You have one interaction here, so you have a term associated with that. You have another interaction here, so you have a term associated with it. You have another interaction here and a term associated with that. So you can look at the total interactions between each pair of particles. There's going to be a certain amount of energy associated with each individual interaction between each single pair of particles. If you add up all the pairs, you have the total energy of interaction of that system. We'll look here at the total energy of an object in a circular orbit. In this case here, we have an object of mass little m is orbiting an object of mass capital M at a distance r with a speed v. So we can say a couple things. We just found the gravitational potential energy. We can say that the total energy of the system is going to be the kinetic energy of motion of that orbiting object plus the gravitational potential energy of interaction between those two. We're assuming here that this object at the center is not moving for the sake of simplicity. So in this case, we have kinetic energy of the small particle, and we also have gravitational potential energy for the energy of interaction between these two. And that represents the total energy of the system. Now, what we can say is that the velocity isn't just some free value. For us to have a circular orbit at a certain distance, little r, not just any value will do. We can say there that we would have to have a centripetal force acting on that little particle with a value equal to mv squared over r. And that centripetal force would come from the gravitational force between the two particles. We can simplify a couple terms here, and we find that that v squared must equal gm over r. I can take this value of v squared here, and I can plug it in over there. There's v squared. And notice I have here g capital M little m over r, g capital M little m over r. I've got half of one of those minus a full one of those. I can factor out that term. And I see that this is going to give me a negative 1/2. So the total energy of my circular orbit is then negative g m little m over 2r. Again, this is a negative quantity, so this is a bound state. An object that is orbiting another object in a circular orbit is bound to that larger object. That's why satellites continue to orbit the Earth. That's why the Earth continues to orbit the Sun. We're in a bound state. We would need some sort of extra energy to pull us off into outer space and away from that orbit that we find ourselves in. We found the total energy for a circular orbit. This is much simpler because it's circular. In practice, most orbits aren't perfectly circular. They are elliptical. This is what an elliptical orbit looks like. For us, in our solar system, the sun is one of the focal points, and the different planets and comets and such have elliptical orbits around the sun. In that case, the math is a little bit more complicated, but the energy is essentially the same. In this case, A is the length of the semi-major axis. It's that length right there. So we see similar behavior. The math is a little bit more difficult. It's beyond the scope of this class, but we get a similar outcome.